In astronomy, absolute magnitude means how bright a star is actually, and not how bright it appears on the sun. So a star can be very far away and is just seen in the night as a very tiny little star. And the absolute magnitude says now how bright is that star actually, and not how bright comes it now up to the Earth. That is according to the page 48 of Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakeshaft. The albedo is the light which is reflected again. So light hits an object, and the light which is when reflected, a fraction of the light which is reflected, that is the albedo. And in space science it can reveal much about a planet, what the surface of the planet is. And that is according to the page 48 of Structure of the Universe, A to Z of Reader's Digest Library of Modern Knowledge, Book 1, Structure of the Universe, written by Ian Ridpath and John R. Shakeshaft. Aldebaran. Aldebaran is a star which is visible. There is zodiac, and that is the combining of 12 constellations which are visible at the night sky. One of these constellations, of the zodiac constellations, these 12, is Taurus, and in Taurus there is now this Aldebaran star, also called Alpha Tauri. It is 68 light years away from the Earth. Now, a star goes through different stages, and the last stage of a star is it to be a red giant. It grows in size to the 10 or 100 times of its size, of the size of a sun, so 10 to 100 times bigger than the sun, and they are emitting a lot of light. And Aldebaran, or Alpha Tauri, is such a red giant. And Aldebaran is the brightest because it is the red giant of the stars of a constellation, of a Taurus constellation, of a zodiac constellation. That is according to the page 48 of the Reader's Digest Library of Modern Knowledge, Book 1, Structures of the Universe, written by Ian Ridpath and John R. Shakeshaft. Algol. Algol is a triple star system, and there are two stars, and they are where one is moving around the other one, an eclipsing binary star. So one star is there, the other one is there, and then one star is moving around the other one. When the star is in front of it, the dimmer one, so the one which moves around, then the light is a little dimmed. When it goes to the side, the full brightness is there. When the star goes behind, then it is brighter, as if the not so bright one would be in front, but it is a bit dimmer, and then again full. And Algol is such a one. It was discovered in 1782, the first one of its kind of these eclipsing binary stars, by John Goodricke, and it's named after an Arabic word, Al-Ghul, which means demon or ghoul. It's also known as Beta Persei. It's in the Perseus constellation. And that is according to page 48 and 49 of Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, book written by Ian Ridpath and John R. Shakeshaft. Alpha Centauri. Alpha Centauri, these are three stars which are very close together, around 4.3 light years away from the Earth. And if someone looks closely with a telescope, they can see that two of them are actually separate one, and there's actually a third one, so these are three individual ones. The third one is called Proxima Centaury. They are together, appear basically as one star, and they are the third brightest star then basically on the sky, but they're actually three. And that is according to the page 48 of Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakeshaft. Altair. There is the constellation Aquila, that is the so-called summer triangle, three stars. Dana, Vega, and then Altair, the brightest one of the three. So Altair is the brightest star of Aquila constellation, consisting of the three stars Deneb, Vega, and Altair, which is also called the Summer Triangle. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakeshaft, on the page 48. Altazimut. That is a mounting which can be added to a telescope so that it is able to be made up and down in altitude and also from side to side in azimut. So basically the Altazimut is just a piece of device in a telescope that can look up and down in altitude and to side in azimut for a telescope to follow the star when it apparently wanders over the sky of the Earth's rotating. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 48. Antares is a red giant which is at the sky at the constellation Scorpius. And that Antares is a red giant which has a diameter, so a size basically, of 250 times the one of the Sun. And the name means rival of Mars because it has a red tint like the planet Mars. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 48. The Aphelion, that is the point at which a thing, a planet, which is orbiting the Sun is the furthest away from it. So something, the Earth is orbiting the Sun, and that point where that orbit is the furthest away from the Sun, that is called the Aphelion. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 48. Apogee. If a satellite is orbiting around Earth, the point where that satellite is the furthest away from the Sun on that orbit, that is called apogee. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 48. Aquila is a bright constellation at the equatorial sky, and the brightest star is Altair. Aquila means eagle. According to Reader's Digest Library of Modern Knowledge, Book 1, Part 1, The Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 48. Arcturus is a red giant, and it is a big and bright glowing one. It has a diameter of 250 times of the Sun, so very, very big. It is 36 light years away from the Sun, and it is the fourth brightest star at the sky visible from Earth, and it's part of a bird's constellation, and birds means herdsman. According to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 48. Aristotle, he lived 350 years before Christ in Greek. He was a philosopher, and he believed that the Earth was round. And he also believed that the Earth would be the center of the universe. And many of his ideas were influential, and most of them stayed unchallenged for the coming 2000 years. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, written by Ian Ridpath and John R. Shakespeare on the page 49. Astronomer Royal is an honorary title in Britain, and from the establishing of the Royal Greenwich Observatory in 1675 through Charles II, the British king at the time, it was always the director of his Royal Greenwich Observatory. And until 1972, where it became, under 1972, it became Sir Martin Ryle of the Mullard Radio Astronomy Observatory at Cambridge. Scotland has also an own Royal Astronomer, and it is the Royal Observatory, Edinburgh. And that is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 49. AU means astronomical unit. It is the distance from the Earth to the Sun, 150 million kilometers. Jupiter has 5, Saturn 9, and Uranus 19, and Neptune 30. And that is according to Cosmic Menagerie by Mark A. Garlick on the page 17. Astrophotography. That is photographing of planets and stars, and it is most often done through telescopes. And most oftentimes with these telescopes are photos made, not looked with a human through it, because firstly, that things like stars or dust clouds or gas clouds or just things with a low surface brightness are visible on long exposure photos, not so good with human eye just looking into it. So long exposure photographs. The second reason is that these Astrophotographies can then look for infrared and ultraviolet light. Human eye cannot see infrared and ultraviolet light of the electromagnetic spectrum, and some stars and so on are emitting these ultraviolet or infrared light. And also, it is better to see on a photo what has changed since the previous photo. For example, Pluto was discovered in 1930 this way by making successively photos of its orbit. And it is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare, on the page 50. Astrophysics. That is about, and that are people who are trying to understand the universe. They are trying to find out what the compositions are of stars or of planets or things or galaxies. And as the laboratory, as the observation thing serves the universe, the nature around them. Because they can just look what is happening there. They are looking in the universe what is happening there under extremer conditions as they are on Earth. Extremer temperatures, extremer densities, extremer pressures. And they're using spectrography, and with that they are looking at different wavelengths of things which are emitted, not just visible light, but also infrared light and microwave light, and the radio waves and the X-rays and the ultraviolet light and the gamma rays. So we're looking at the whole spectrum, what something is emitting, and they are trying to find out what quasars are, radio galaxies. And we're also using radio signals, and with that we're trying to find out more about quasars and radio galaxies, and also other things that we're using. And we're trying to find out how, with atomic physics, for example, we're trying to understand how atoms are formed. They found out that most of the universe consists out of hydrogen and helium, and all the other elements, all the other ones, are not so much existing, and we're trying to find out how it works. And atomic physics brought some explanation how out of hydrogen comes helium and so on, and the other elements, and how stars are living, what the life cycle of the stars and so on. We're trying to understand the structure, the future, the origin of the universe, and all its elements. And that is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare, on the page 50. Auriga is a star constellation, and it can be seen in the winter in the northern hemisphere. And it is between Gemini and Taurus at the end of the Milky Way, and the brightest star is Capella. And Auriga means charioteer, and a chariot is a vehicle drawn by horses. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare, on the page 50. Baily's beads. Now, Francis Baily, he lived in the 18th century. He was one of the founders of the Royal Astronomical Society in England. Now, and he pointed out that the moon is something visible by total eclipse. So the Earth is standing here, and when the sun is here, the sun is shining on the day, and when the moon comes into the middle, and now suddenly the sun is by total eclipse totally blocked by the moon. Happens not so often, but it happens. And now Baily's beads, these are when the mountain peaks at the moon. So some mountains are standing up at the moon a little bit, it's very, very small, and then through them the last sunlight is going through them. And that was pointed out by Francis Baily, and therefore these mountains, through which mountain peaks the sun is shining for a little moment, are called Baily's beads. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare, on the page 50. Barnard's star. It is a star which is 6 light years away from the Earth, and counting Alpha Centauri, the 3 stars of Alpha Centauri as one, it is the second closest to Earth. It was discovered by Edward Emerson Barnard in 1916. Proxima Centaury is a red dwarf, and that is one of his triple star system of Alpha Centauri, and also Barnard's star is a red dwarf. So they are both not visible from Earth with a naked eye. Now red dwarf is visible with a naked eye from the Earth out. Proxima Centauri is the closest one because that is 4.2 light years away from the Earth. The other 2 stars which are visible from Earth are 4.3 light years away of a triple star system, Alpha Centauri, and now Barnard's star is 6 light years away. And it has a lot of proper motion, the Barnard star. It is the star which the most known proper motion of it. In 180 years, it moves on the sky as much as the moon is visible on the Earth. So proper motion is the Earth is moving in the space, and also the Barnard star, for example, is moving in the space, that we're moving around, and they're changing the position which we have on the sky, and the constellations are shifting and so on. And that is a lot by this Barnard star. It is in 180 years, as much on the sky moving to the side as the moon is taking space as it is visible from Earth. And then already when no other planets were discovered, apart of the one in the solar system, it was suspected that the Barnard star has planets because there's little wobble in it visible. And that could be the cause, that is the reason for the suspicion why it has planets, because there are planets in the size of Jupiter, two of them, circling around it. And that would have a little influence on it where it goes. And then it would wobble a little bit. And that is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 50. Betelgeuse. That is a red supergiant star. And it is in the constellation Orion, and it is hundreds of times larger than the Sun, and it is varying in diameter and in brightness. And that is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 50. Bode's law. There was in the 1800s Johann Orlando Bode, and in 1772 he said all the planets are in a specific mathematical pattern away from the Sun. And he said always starting with 0. So 0, 3, 6, and then always starting 0, 3, 6, 12, 24, 48, 96. And then that number plus 4. So not 0, but 4. 0, 3, 6, 6 plus 4, 10. And that was basically what he said. The first planet, Mercury, is away 0 plus 4, so 4. 0.4 astronomical units. And the next one is when the 0, 3, 6 plus 4 would be the first one already. So the Earth, the third planet. Venus then 0.0, 3, 0 is the first one, so 4. 3 plus 4, 7. And Earth then is the 10, so 10 is 1.0. The Earth is 1 astronomical unit away from the Sun. That is the measuring. The measuring of 1 astronomical unit is saying the distance of Earth to Sun. So it fits exactly. The first one, 0 plus 4, Mercury 0.4 astronomical units. Next one, 0, 3 plus 4, 0.7. Venus is 0.7 astronomical units away from the Sun. The Earth is 0, 3, 6 plus 4, 10, 1.0 astronomical units. And so on. 0, 3, 6, 12. And when we're with 12, it would be on 16, the next planet, Mars, 1.6. And basically it works all like that. Then with the next planet, then with other Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and also Neptune. Basically works out. All this doubling, 0, 3, 6, 12, and then 24, and 48. So 48 astronomical units plus 2 is 52, would be when Saturn, Jupiter, something, away from the Sun. That is basically Bode's law. Idea was it always doubling plus 4 in astronomical units are away from the Sun. And that's according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structures of the Universe by Ian Ridpath and John R. Shakespeare on the page 50. Edward Emerson Barnard. He was born in the year 1857, and in the year 1892 he discovered the fifth moon of Jupiter. It was the first time that the moon of Jupiter was discovered since Galilei had done it 300-400 years ago. And in 1916 he discovered a planet. That planet has its name after him, Barnard's planet. It is 6 light years away. The closest planet to the Earth is Alpha Centauri, 4 light years away. And he was also a pioneer in astrophotography, so making photographs of planets and stars in the universe and observing that and analyzing that. And he was charting in detail dark clouds of gas in the Milky Way. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare on the page 50.
You want to stand up in the morning with your right foot. So in the morning you point with your right hand to the sun. The left side is east, so west where the sun is, and east, and you're looking to the north. In the evening it's the other way around. So you put your left right hand to the sun, the left hand is east and facing north and south behind you. The evening, which happens right now, left hand to the sun, right hand is east, you're facing north, it goes up and down to the south.
About 8 minutes and 20 seconds needs the light to travel from the sun to the Earth. It's not every day the same. Around the 3rd January, the Earth is closer to the sun and the light is around 2 seconds faster than on around the 4th July, when the light takes around 2 seconds longer. Friedrich Wilhelm Bessel, he was born in 1784, and in the year 1838 he calculated how far a star is away from the sun, 61 Cygni. And he did that using the Fahrenheit method. Now it works like that. Basically how it works now in small, if you hold your thumb out close to the eye and you look now with one eye and the other eye, when you see the thumb in front of a 4 or 5 meter away background jumping a meter. If you hold your thumb completely out with your arm and you switch and look always with one eye, you can see it switching just around 10 centimeters apart. So the further the object is away from which you change the angle of looking at it with the eyes, the less it jumps. So you have it very close, and the angle changes now dramatically, and you see a completely different background basically. If you have it far away, it jumps just a little bit from side to side. Now the Earth is rotating around the Sun once a year. So 6 months later, the Earth is on the other side. So if the people on the Earth looking to a star by seeing it in that angle, 6 months later they've changed the angle. Just if looking with the eyes on the other side, the Earth is changing. And if one now looks, the background switches as well. If a star is very close to the Earth, and the people looking from near to the Earth, they see that background. And 6 months later, they're looking from here and they see that background. So very far away. If a star is very far away and they look, they see just a tiny bit of switch in the background. It jumps just a little bit. And basically with these things it can be calculated, and that switch is called the parallax. With that difference it can be calculated, is the star pretty close, because there's a big switch in the background, or very far away, because there's just a very little switch in the background. It works until 100 light years away, when the Seyferd variable is used. Seyferd variable, these are stars which are getting brighter and not so bright, always in fixed periods, and the longer the period takes, the brighter the star is. If it takes 1 day, it is not so bright. If it takes 10 days to go full brightness and lowest brightness, it is a very bright star. And with now measuring around knowing how big how big that brightness is by knowing it is 10 days and not 1 day, with comparing it to how bright it appears on Earth, it can be calculated how far it is away. So see the variables. It goes brighter and not so bright. So it is able to measure how bright is it actually. If it takes 10 days, it is very bright, 20 days even more brighter, 30 days even more brighter, 2 days not so bright. And when it's looked how bright it appears it on Earth, the stars don't appear so bright on Earth because they're very far away. Comparing these two measurements, knowing how bright is it actually, because the longer it takes to get bright and not so bright that can be seen on Earth, it is known how bright it is. Comparing it with how bright it appears on Earth, and we now know for stars which are more than 100 light years away. But for less than 100 light years, this method works with looking with the angle, very close, big switch, very far away, small switch. And that can be calculated and heated. And that is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpeth and John R. Shakespeare, on the page 50. From neutron star to black hole. A neutron star is a massive star which had gone through a supernova explosion, followed by a gravitational collapse, by which the massive star was compressed and had reached high density. The high density causes the electrons and protons to combine to neutrons. After the massive star had had its gravitational collapse, which made it a neutron star, something referred to with neutron degeneracy pressure partially prevents the neutron star to collapse again. Additionally to the neutron degeneracy pressure, some other thing referred to with repulsive nuclear forces somehow supports the neutron star against collapsing. The so-termed Tolman-Oppenheimer-Volkow limit is 2.2 to 2.9 solar mass, and says that the neutron star with a mass of 2.2
to 2.9 times of the mass of a sun will collapse to a black hole. So the neutron degeneracy pressure and repulsive nuclear forces may prevent a neutron star with less than 2.2 to 2.9 solar mass from collapsing to a black hole. But if a neutron star has more than 2.2 to 2.9 times the mass of a sun, it will collapse and form a black hole. A massive star can have a supernova explosion followed by a gravitational collapse, compressing it to a neutron star. And if the mass of a neutron star is 2.2 to 2.9 the times the sun has of mass, neutron degeneracy pressure and repulsive nuclear forces are no longer sufficient to prevent the neutron star from collapsing. And the neutron star collapses and forms a black hole.
IC1101. IC1101 is the name of the largest so far found galaxy. And it is 50 times larger than the Milky Way. The Milky Way is the galaxy in which the solar system of the Earth is. And already in the Milky Way, the light needs 100,000 years to travel from one side to the other one, and that IC101 is 50 times larger. The Milky Way has already 100 billion stars, and that IC101 has 100 trillion stars. That is according to Isabel Thomas out of his World Book, page 30.
Info snippets to astrophysical jets. Astrophysical jets are an astronomical phenomenon. Astrophysical jets exist by so-called supermassive black holes. Astrophysical jets can occur besides of by supermassive black holes by quasars, radio galaxies, or within galaxy clusters. By astrophysical jets, something is emitted. Ionized matter is emitted through astrophysical jets. Supermassive black holes, quasars, radio galaxies, or within galaxy clusters, ionized matter can be emitted through astrophysical jets. If the emitted ionized matter is so fast emitted by the astrophysical jets that the speed of the emitted ionized matter is close to the speed of light, the astrophysical jets are called relativistic jets. There are some ideas how astrophysical jets happen. One try to explain astrophysical jets is that inside of a black hole, magnetic fields are tangled. The idea is that they are tangled in a way that if ionized matter is emitted through them, the ionized matter comes not irregular at different sides out of the magnetic field, but only through a narrow beam. By this explanation try, the magnetic fields would be tangled along the diameter of the black hole, and the ionized matter would come out through astrophysical jets at both ends of the diameter of the black hole. Info snippets to neutron stars. So-called massive stars exist. A massive star can explode. The explosion of a massive star can be a supernova explosion. After the massive star had a supernova explosion, a so-called gravitational collapse can happen. During a gravitational collapse, the star is compressed. When a massive star has after a supernova explosion a gravitational collapse, the star is compressed. Because the star is compressed after the gravitational collapse following the supernova explosion, it reaches a high density. A neutron star is a massive star which had a supernova explosion followed by a gravitational collapse which compressed the massive star. Neutron stars don't generate heat anymore and they cool down. It is assumed that neutron stars are mostly composed of neutron because the extreme density through the gravitational collapse after the supernova explosion had caused the electrons and protons to combine to additional neutrons. A neutron star can collapse further into a black hole. New neutron stars are very hot. The cooling down process takes many million years. Neutron stars can rotate several hundred times per minute. Info snippets to pulsars. Neutron stars exist. A neutron star can rotate. A rotating neutron star can be magnetized. A magnetized rotating neutron star can have magnetic poles. Out of magnetic poles, electromagnetic radiation can come. A magnetized rotating neutron star can emit electromagnetic radiation out of its magnetic poles. When a magnetized rotating neutron star emits electromagnetic radiation out of its magnetic poles, it is called pulsar. A pulsar is a magnetized rotating neutron star which emits electromagnetic radiation out of its magnetic poles. The electromagnetic radiation can be on Earth observed if the electromagnetic beam exiting the magnetic pole of a magnetized rotating neutron star shoots into the direction of the Earth. Because the electromagnetic beam exiting a magnetic pole of a magnetized rotating neutron star can only be observed in pulses whenever the beam points to the Earth, it is called pulsar. Pulsars are very dense and are having a short and regular rotational period. Because the rotation of pulsars are so regular, the pulses of electromagnetic radiation are also regular. The pulses of the electromagnetic radiations can have intervals of milliseconds to seconds. Because the pulses of electromagnetic radiation are so regular, they can be of use for astronomers. Pulsars are a source of so-called ultra-high energy cosmic rays. Observing of a pulsar in something referred to as binary neutron star system was used to indirectly confirm gravitational radiation. Info snippets to superluminal motion. Superluminal motion is part of astronomy. Energy exists. Bursts of energy can be emitted. Bursts of energy can be emitted in so-called radio galaxies. Bursts of energy emitted by radio galaxies have a speed. Light itself has a speed. The speed of the bursts of energy which are emitted by radio galaxies can appear to be faster than the speed of light. It appears that the burst of energy coming out of a radio galaxy is faster than light. It is motion which appears to be superluminal. Superluminal motion is the motion of energy bursts coming from radio galaxies which appears to be faster than light. Beside of radio galaxies also, BL-like objects, quasars and blazars can emit bursts of energy with superluminal motion. It is thought that radio galaxies, BL-like objects, quasars and blazars contain a black hole, which is responsible to emit energy bursts which appear to be faster than light.
With Il Giorno di San Giovanni is St. John's Day meant, which falls on June 24. Midsummer is celebrated around the date of a northern solstice, that is when the daylight is the longest, June 20, 21, 22, which was traditionally reckoned to be June 23, 24. The festivities of St. John's Eve, June 23, and St. John's Day, June 24, and the traditionally reckoned northern solstice and therewith midsummer are closely associated.
Next to that airplane there is the moon, and it's a starting full moon, so when it starts it has that shape like a right hand, but gets closer than the left hand. Is when we mean. So a full moon comes with the right hand first the shape, and it goes away with the left hand.
Proxima Centauri. Proxima Centauri is a part of the Sun, the closest star to the Earth. It is 40 trillion kilometers away from the Earth. The Sun is 150 million kilometers away. With a spacecraft, it would take thousands of years to get there. It is a fairly small and dim star, so that it can't be seen with the naked eye on the sky. A telescope has to be used. And that is according to Isabel Thomas, Out of This World, on page 31. Seyferd Galaxies are a type of galaxy. They are spiral-shaped like the Milky Way. They are basically round with arms to the side. But they are emitting 100 times more energy than the solar system, than the Milky Way with the solar system in it. And they are bright. The nucleus in the center is bright. And it is believed that they are a stage between galaxies like the Milky Way, in which the solar system is in. So big Milky Way with the solar system with the Earth in it. There is a stage between normal galaxies like the Milky Way and quasars. Quasars are much smaller, just 1 light year across, and they are very bright and emitting a lot of energy. And these Seyferd galaxies are somewhere in the middle between them. If there's a link, if there's a stage where it's not completely understood in this book, if they are a phase or whatever of this type, but they're basically a middle part between galaxies like the Milky Way and very bright quasars, which are emitting a lot of energy. They are named, these Seyferd galaxies are after Carl Seyfert, an American person who in 1943 discovered them. And that is according to Structure of the Universe on the page 67 of a Reader's Digest, Library of Modern Knowledge, Book 1, Chapter 1, written by Ian Ridpeth and John R. Shakespeare. Sir George Biddle Airy. He was born in the year 1801, and he was the Astronomer Royal of Britain from 1835 until 1881. In the year 1880, where he introduced the Greenwich Mean Time, and that is the official time of Britain. And in the year 1884, so a little after he left office, there was now, at the place of the observatory in Greenwich, the zero line on longitude drawn at that meridian on which the time shifts are based for the clock. So around 2,000 kilometers at the equator when the clock is 1 hour more in front. And that is according to Structure of the Universe A to Z on the page 48 of a Reader's Digest, Library from the Modern Knowledge, Book 1, written by Ian Ridpeth and John R. Shakespeare. Sir Isaac Newton, he studied at Cambridge, and his most famous work is Philosophia Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, and that was about gravity and how it applies to the whole universe. He also discovered that light has not just the color of light, but that it is composed out of multiple different colors. And his ideas are still important for the world today. And he was a member of the Royal Society, which was formed by Charles II. Sir Isaac Newton, born in Lincolnshire in England, 1643-1727. And that is according to the Life in UK Test Handbook, page 30 and 31. Spiral, lenticular, elliptical, and irregular shaped galaxies. They are the spiral galaxies. They basically look like a star which is turned and the arms are hanging behind. And when they are the lenticular galaxies, they are looking a bit like the lens out of a magnifying glass. And then there are the elliptical galaxies, they are oval, almost like an egg. And then there are the irregular shaped galaxies, they are irregular shaped. 2/3 are the spiral shaped ones, the turning ones with these arms out, and the Milky Way is one of these spiral shaped galaxies. That is according to Out of This World by Isabel Thomas, page 33. Protostars. So there is just a big cloud of interstellar fog, of a giant molecular dust cloud, basically. And at some regions, this patchy whatever is more denser, and there is a higher gravitation, and it pulls them more together. So at some places, this big cloud has more material, more mass, and it pulls them in because it has a higher mass. And the more it pulls in, the higher gets the mass of it, and the stronger can it pull in with gravitational force. And that's how things starts then to turn. It starts to circle, and through that to flatten out. And after that takes around for 1 million years, then we're having a protostar. And this protostar now has in the middle a gaseous clump in the core in the middle. And the whole thing is now called a globule and a protostar. So in the middle there's now this gaseous clump. And now it's a protostar. And now for 100,000 years this gravitation continues. And then in the center it has gotten warm enough. It falls in through the gravitation more stronger and stronger, pulls it together. And this is energy of motion, so there's something moving, and that is called kinetic energy. And this kinetic energy, because it falls in stronger and stronger, is then present in the form of heat, and it gets warmer and warmer. And then after 100,000 years of being a protostar, the birth cocoon, the gaseous clump, starts to vaporize. And when this gravitational contraction continues for a million years, and so when the birth cocoon has vaporized, it reveals itself as a glowing, luminous, red ember-like mass to the universe. Now, and then for 1 million years it continues its gravitational contraction, and the thing heats up that protostar up to 5 million degrees Celsius. And that is basically then the end of the protostar phase. Then comes the T-Tauri phase of the star developing. And that is according to Mark A. Garlick's Cosmic Military book on page 34. The T-Tauri phase of star formation. Now, after the star had been a protostar, it is now in the T-Tauri phase. It has in the center 5 million degrees, but it has at the surface just 4,000. It is still not hot enough for the thermonuclear reaction with making in the inside of the pressure of all the hydrogen atoms together to form helium. It's not hot enough for that. But the gravitational contraction continues, that's all. But now the point is, it has already 4,000 degrees at the outside, so it got hotter and hotter during the protostar phase, with kinetic energy more pressing together through the gravitational contraction just by itself, basically. Now, in these 4,000 degrees also at the surface lead for the gases in all it to become ionized, to become ions, to become basically plasma. Now, it happens like that. Gas is normalerweise neutral. And now it happens that they are shaken apart through the heat, and my interpretation is that these atoms have in the center the protons with the same number as electrons on the shells on the outside. Now, if it gets too warm, the valence electrons, the electrons one electron at the outside, is shaken apart because it's so hot. It loses that one electron. It's just too hot, and it bursts basically. It falls apart, and it loses one electron. And through that, every atom has the same amount of protons in the center as electrons, and is therefore neutral. But now it has lost an electron. It has now one proton more than electrons, and it is now positively charged. It is no longer neutral. So this process is an ionization, and all these atoms, because it's 4,000 degrees hot, all these gases are suddenly no longer neutral, but electrically charged. Now, the T-Tauri star, in its formation, is bigger than the Sun, and it's also rotating faster. And all these electrically charged particles, or gases, are now rotating, and a rotating electrically charged thing is an electrical current, basically. The thing is basically an electric current, and every electric current has a magnetic field. And this magnetic field now goes through the space. Around it, it has also a global magnetic field. It goes then also around the space through the protoplanetary disk and sucks out all the gases with its magnetic field. And at that point where they hit when the T-Tauri star, there's no violent reaction. And that is one of the hallmarks of the T-Tauri star phase of a star. And they're also bursting out of flares out of these T-Tauris also. That's also a thing. And that is according to Mark A. Garlick's Cosmic Military book on the page 37. The main sequence of suns. The point is that the T-Tauri phase after the protostar phase of a star has ended. And that had happened because the star has reached 10 or 15 million degrees Celsius. And that makes now thermonuclear reactions possible. Previously in the T-Tauri phase it was just 1 million degrees or a bit more, and then we also had 4,000. Enough to ionize the gases, so basically that we're losing an electron, and that the star was turning, so it was a big turning electromagnetic current. Now it's way hotter, 10 million degrees or 50 million degrees, and a thermonuclear reaction can happen. And inside of the star, by these 10 million degrees, it is so hot that the positive hydrogen atoms are moving so fast that they're overcoming their electrostatic repulsion. So they are repulsed, they don't want to come together, but now it's so hot that they're moving so fastly that they're sticking together. And they are forming a new element, helium. And that stellar nucleosynthesis causes now that there is an outward pressure. So the forming of two hydrogens together to a new helium causes now with stellar nucleosynthesis, which has an outward pressure, and the hydrostatic equilibrium happens. So basically there's so much outward pressure as there is pressure to the inside from the gravitation. So the sun is putting together. It did it in the previous parts with the gravitational constriction. It's just start like that, just a bunch of dust pulling together stronger and stronger, and then loading it up with kinetic energy more and more hotter and hotter. Then it was so hot with the gas to ionize with the magnetic field, and now it had become even more hotter. The gravitational contraction has stopped because it's now so hot that there's an outward force through this fusion of hydrogen together to helium. And that can last, that is the longest phase of a star. By the sun, it lasts for 4.5 billion years already, and it's going to last again so long. It can be faster if it's a bigger star or sun, because then the pressure is higher, and the hydrogen is fusing faster together to keep the outward pressure standing. And it can be slower if the star is much smaller. I mean, it's going way smaller when the hydrogen is formed. And also, by these red dwarfs, it goes to the outside, cools down, goes in again, and also all the hydrogen in the outside of the sun is used up. So the main sequence, it is much pressure to the inside, very hot in the middle, and where the hydrogen is pressed together, forms new helium, which makes an outward force, and that is basically the hydrostatic equilibrium with this whole thing. That is according to Mark A. Garlick's Cosmic Mimicry book on the page 38 and 39. Flare stars. In a star, there are some gases, and they're getting hotter because it is pressing together through its own gravitational constriction, because it's pressing onto itself, it's falling onto itself. It gets hotter. And when it gets a bit hot, then they're ionizing, and they're becoming plasma, these gases. They are losing an electron. They shatter apart. It's hot, but they shatter apart. Normally, atoms are neutral. They have the same amount of protons as electrons on the shells. They are neutral. Now they lost an electron, and now they have too much protons than electrons, so they are too positive. And they are no longer neutral, but they're now a positive, negative charge technically. A positive charge, no. And such a star is circling. And whenever something is circling which has an electrical charge, which it has because it's not positive, that has a magnetic field. Every current has a magnetic field. That thing has no magnetic field, such a star, a T-Tauri star, a neutron star, or here flare stars. In flare stars, there accumulates this magnetic field, this force, this energy under the surface, typically near the sunspots. The sun has, but also these are the solar flares. So the energy is accumulating and then suddenly bursting out. All this magnetic energy is bursting out. And that has a lot of energy. It can be 6 septillion joules of energy. That is a very big number. Or 160 billion megatons. And it bursts suddenly out. One of these stars is UV-CT. And if that thing has its flare episode, it gets 75 times as bright as usual. And it happens only in stars which are quite cool, so that it can accumulate. It's accumulating, they're not so hot, not so much radiating, they're quite cool, and then suddenly it bursts out. For example, Proxima Centaury, which is a red dwarf, so a bit slow burning star, and then suddenly it bursts out. And that is according to Mark A. Garlick's Cosmic Mimicry book on the page 56. Red dwarfs. Red dwarfs are just suns in their main sequence. They are just doing the thermonuclear synthesis. They are just doing the stellar nucleosynthesis, the thermonuclear reactions. Inside of them, it is warm and hot because the pressure is pressing together, and the two hydrogen are overcoming, because they're so hot, their electrostatic repulsion. They're sticking together, forming helium. Red dwarfs are much smaller, and therefore this gravitational pressure, which makes the heat in them and so on, is much smaller, and this happens much slower. Therefore, they are not so bright. They have less luminosity, they have less mass, therefore less gravity, and also a smaller diameter. So they're much smaller, less bright. Inside of them, this stellar nucleosynthesis, two hydrogen pressing together to become helium, is not happening so fast. And another reason is the heat rises up and then cools down and it goes down again. So the hydrogen from the outside is also used up. In a bigger star, where the hydrogen at the outside is almost never used. It's just in the center, at one time all used up, when it goes a bit together. And when it goes together, some hydrogen is, because the gravity is still so strong, but in the middle is now, the thermonuclear synthesis is no longer happening, because there's no hydrogen anymore used up, and it goes together. And there's no pressure to the outside through this stellar nuclear synthesis. And it collapses basically. When it collapses, some hydrogen comes again into the center, enough pressure, new one, it expands and so on. But basically, most hydrogen is never used up in bigger stars. Red dwarfs use it all up. The heat goes up and cools down and sinks again down, and the hydrogen, basically the whole thing is churned through completely, and all the hydrogen of a red dwarf is used up. And that makes it that such a red dwarf, for example, Proxima Centaury, lives 1,000 times as long as the Sun, which is 300 times as long as the universe is existing. A trillion years, what would it be? Now, so red dwarfs, there that happens much slower because they have much less pressure. And they are not so bright. Proxima Centauri is the closest one to the Earth. It cannot be seen with the naked eye. It is 100 times too faint to be seen with the naked eye from Earth. 80% of stars out there are red dwarfs, or 80% of the stars closest to the Sun are red dwarfs. And no one can be seen because they're too faint. Because inside of them the pressure is too low, because they're too small, the hydrogen is pressing not so fast together, not so much luminosity. That is according to Mark A. Garlick's Cosmic Planetary book on the page 40 and 41. BE stars. These are stars which are spinning so fast that they're getting oblate. So the equatorial zones are through the centrifugal force going to the sides. It happens also a bit with Saturn and Jupiter, the two gas giants. Saturn, for example, it spins in 10.6 Earth days, but it's way bigger than Earth, so it's spinning pretty fast and it's out of gas. And there also, it's 10% bigger the distance when from the sides than it is from pole to pole. And one of these stars, for example, is Arcturus, which is such an BE star in the Eridanus constellation. It has 3,000 times the luminosity of the Sun, and it is 7 times as big. And that thing is so much oblate that it is 56% longer in the center than pole to pole. And the poles are through that much closer to the center where the nuclear reactions happens with the hydrogen fusing together to become helium. That is way hotter there. 20,000 at the poles, 10,000 at the equatorial zones. And they oftentimes have a vast, thin gas cloud around them. And magnetic fields also play a role in it, how they are around these vast, thin gas clouds. And that is according to Mark A. Garlick's Cosmic Planetary book on the page 54 and 55. Supergiants. These are stars which are bigger, 8 times as big as the Sun, or even more. And they are burning just like a normal Sun, but a little bit differently. Now, they are technically smaller than other stars. The Sun will come into its red giant phase. It will happen like that. In the inside, the hydrogen will be used up, and when there's no outward force anymore, the fusing of hydrogen in the center together creates an outward force. Once the hydrogen in the center is used up, then it breaks in, there's no outward force anymore. When it breaks in, hydrogen which was at the outside comes closer to the center and cannot used again. And now it falls together, the outside comes in, and now it starts when it comes in from the outside again to open again. And that way the Sun will reach 200 times its size. So it shrinks, and when it comes closer to the center, it opens again, 200 times its size. So such a supergiant has 25 times the size of the Sun. The Sun will reach in its red giant phase 200 times of its current size. So a supergiant, or a blue supergiant also called, is smaller as a normal star will be in its red giant phase. But a supergiant or a blue supergiant will reach its red supergiant phase as well. They are already 10,000 or a million times brighter as normal stars. So supergiants, 8 times bigger, 25 times as big, and 10,000 or a million times as much brightness as a normal star. A star will reach in its red giant phase, when it gets bigger, 200 times its size, as it has currently. Such a supergiant is already 25 times as big. It can get 2,000 times as big as the Sun. So very bigger. When it reaches its red giant phase. Now it can get so big when basically that it is exploding itself technically, or something like that. It is bulging up, billowing up, and then it is so much bulged up that it loses its outer sides. And when it shrinks again, it gets again colder. So such a supergiant or a blue supergiant can get so big that it loses its outermost parts, loses something, and gets again smaller to become again a blue supergiant. So they can change between a blue supergiant, a red supergiant, blue supergiant, a red supergiant, and so on. These are supergiants. Just the same as stars, just bigger. And if they come then in the upper phase, in the red supergiant phase instead of red giant phase, making it so big that you're losing something and going again back to the blue supergiant phase and back again. It's the same with the phase that just the hydrogen from the outside comes again into the center and can fuse again. And that is according to Mark Egalic's Cosmic Mechanical book on the page 46. Brown dwarfs. A normal star comes about if there's a lot of interstellar dust just pulling itself together stronger and stronger, and it puts itself under so much pressure together that it reaches 10 million degrees Celsius. And when hydrogen in it can be fused into helium, that helping an out radiation, and it is a burning glowing star. These brown dwarfs never had enough dust to form enough pressure to form 10 million degrees. The pressure comes basically from itself contracting. It doesn't reach 10 million degrees, just 5 or something, 5 million degrees. And that isn't hot enough to fuse hydrogen together to become helium. They are not burning like a star. But 5 million degrees or something, which they sometimes reach, is enough to fuse the deuterium together. The deuterium is a form of hydrogen to make then helium-3, a form of helium, an isotope of helium. And that gives it also a bit glowing. It's like a faint star. And if they're a bit more massive, then we can fuse lithium together to form actual helium. And that is what brown dwarfs are. They are around the size of Jupiter, maybe a bit bigger, but a lot denser. They can have surface temperature at freezing point, so not like stars hot, but at freezing point. But they can have also up to 2,500 grams for surface temperature. So actually like a little star, which is a bit cooking. Not really, but a bit cooking. And they can have weather phenomena. They can have storms and clouds out of hot grains and sand and iron. That is according to Mark Egalic's Cosmic Mechanical book on the page 58. Subgiants. Now, after a star had gone through its main phase, in which in the inside it was hot enough with 10-15 million degrees Celsius, that two hydrogen atoms are having overcome their electrostatic repulsion, and they were able to stick together and forming that way helium. Now that had ended because the hydrogen in the center all had fused to helium, the hydrogen left. And there isn't enough power, enough pressure from the outside, enough heat to make the same number for helium, to press two helium together, but it isn't working. So the hydrogen is used up, fuel is gone. What happens now? It falls together. By this stellar nuclear synthesis, when the two hydrogens were pressed together, there was at the same time an outward force happening, bringing that star, that sun, into a hydrostatic equilibrium. So there was the same pressure basically from the outside with the gravitation as there was from the inside out through this fusing of hydrogen to helium together. Now it doesn't happening anymore, and the star is collapsing on itself basically. But there is still hydrogen in the outer surfaces of the star. Only the hydrogen in the center was used up. On the outside it is still there. And now it falls together. And now during its falling together, the hydrogen from the outside comes closer to the center. And it is able then, because it's closer to the center at hotter regions, to do again our thermonuclear reaction. And the hydrogen of the outside comes a bit to the center, two hydrogen coming together, and we're creating again this outward force. So the core is shrinking and also heating up, and the outside is technically also shrinking, but because when there is happening that thermonuclear fusion, the stellar nuclear synthesis, two hydrogen, one helium, it is expanding. So the core is shrinking and the outside is expanding. And it is expected to last by the sun for 700 million years, this phase of a core shrinking, heating up. Overall the star gets cooler, but the outside is bulging up, and the sun is expected to reach the 3 times its size through that. And that is according to Mark Egalic's Cosmic Mechanical book on the page 42. Giants. Now it was so, before we were giants, there were subgiants. And where the hydrogen in the center of suns was used up. And previously in the main sequence of suns, the longest phase, where the hydrogen in the center is so hot at 10 million degrees Celsius, but it's moving so fast that it is overcoming its electrostatic repulsion. The hydrogen doesn't want to come together. But it is so hot that they're moving so fast that they come together, fuse, and becoming helium. So two hydrogen coming together to helium. That thing, that nuclear synthesis, that stellar nuclear synthesis, creates an outward radiation force. And that keeps it in balance, the star. There's pretty much the same force of gravitation to the center as there is through the thermonuclear reaction with stellar synthesis to the outside. Now there's no hydrogen anymore left. All the hydrogen was fused together to become helium. And the core starts to shrink. There's no outward force anymore. It shrinks. While it shrinks in this subgiant phase, the hydrogen that was on the outside. And the inside is all used up, but on the outside is still hydrogen. It's coming closer to the core, and it is enough pressure and again and heat to come again together with hydrogen and expanding. So the core is shrinking, the outside is also shrinking, but when the hydrogen comes together and is expanding again from the outside. All over, the core is shrinking, the overall dimension is expanding. And what is happening now? Now the core is shrinking and the core gets hotter because it's shrinking. The core shrinks and the core reaches 100 million degrees Celsius. And now it's hot enough, not just for the hydrogen to fuse together, that was 10 million degrees. Now the hydrogen is used up, the helium can fuse. There's a lot of helium ash, a lot of helium after the hydrogen is fused. Now at 100 million degrees, after it had contracted more and more, the helium can fuse to become carbon and oxygen. And again, it starts from the beginning and an outward force is happening again. Now the helium is fusing at 100 million degrees Celsius, an outward force is created and it puffs off the outer layer, expanded layers as a planetary nebula. The thing gets even bigger and puffs out a part of it. Now it's a giant. And these giants, they are 1,000 or 10,000 times as bright as a normal sun, and they are also tens or hundreds of times bigger as normal suns. The sun is expected to do it also. After some time, it's in its main sequence, it will come into its subgiant phase, it will come together, the outward is expanding, and suddenly at the center it's hot enough, the helium is fusing together, and an outward force, the thing will expand to 200 times its size. There are also blue ones, not all are red. Now, that is according then to Mark A. Garlick's Cosmic Minigery book on the page 44 and 45. White dwarfs. A sun or a star came out of its main sequence. In the center it was hot through the pressure enough to make hydrogen together to form helium, and while this thermonuclear reaction happens, there's an outward force. Now all the hydrogen in the center is used up and the star just pressing together, there's no outward force through the thermonuclear reaction anymore. Now the next phase starts, the subgiant phase. The core shrinks together, from the outside also shrinks it together, but now hydrogen, which was at the outside, so was not used in the center, comes closer to the center. It is now hot enough, fused enough together, forms new helium, and the core is shrinking, the outward side is rising. And then comes the next phase, the giant or red giant phase. And when it happens with the core shrinking more and more, and when the core has reached 100 million degrees Celsius, because the core is shrinking more and more, there's no outward force anymore inside the core. At the outside, yes, so the outside is growing, the inside is shrinking. When the inside has shrunk enough and has reached 100 million degrees Celsius, inside of it, the helium starts to fuse together. So hydrogen could fuse at 10 million degrees Celsius by main sequence stars, normally stars. Now 100 million degrees have happened and helium is fused together. That has again an outward force, and what has gotten so big during the subgiant and the red giant phase is blown away into a planetary nebula. And basically now all is used up, all is blown away, all is used up, and in the center just stays the core. It uses everything up, and so on. And over hundreds of millions of years, the core is shrinking just until it's very, very close together, the size of a normal planet basically, but it has 200,000 times the size of it. Oh, sorry. And basically the outside was blown away, used up, blown away, and the core is just the core left, shrinking more and more together, becoming incredibly dense, and the electrons are getting degenerate. The electrons of the atoms are completely pressed together, and that is it. The star cools down, gets cold, then over hundreds of millions of years it doesn't emit any light anymore. It's called a black dwarf. It's just the core, incredibly pressed together, without any reaction, without light, without heat. And that is according to Mark A. Garlick's Cosmic Minigery book on the page 48. Black dwarfs. There's a normal star burning. In the center it is 10 million degrees or more, and 4 hydrogen atoms are fused together to form helium, and that generates an outward force. After some time, all the hydrogen in the center is used up, and the star shrinks. Through that, a little bit comes more into the center. A little bit new hydrogen from the outside comes into the center, and as soon as that hydrogen from the outside comes closer to the center, it is able to fuse again because it reaches this heat through the pressure, and it expands again. The core is shrinking, the outside is expanding. When after some time in the core it is 100 million degrees Celsius, and now helium can fuse together. It was previously hydrogen by 10 million degrees. 100 million degrees Celsius, helium is fusing together and to carbon and oxygen and having an outward force. The outward things which have expanded. So they've gotten closer from the outside, and when they have gotten closer, they have expanded. The whole thing had already expanded. Suddenly there is again an outward force because suddenly the helium is fusing and it blows away all the outside things to the planetary nebula away. That goes over a few 100 million years on, and when all the helium is used up and all is blown away, and just in the center is there standing this white dwarf. Just the center. It is hot, emitting some light, and it's just there. But it has lost almost all of it. It has burned it all up, lost it, and now it's just cooling down. And after it had cooled down, after tens of trillions of years, tens of millions of trillions of years, after a very, very long time, there is no outward force anymore, no fusion anymore. It is just standing there with core together, completely shrunk together. All the atoms standing with the electron shells completely together, just standing there like that around, cooling completely down. Nothing happens anymore. It is a black dwarf. No light, no heat, nothing. It's just all the atoms standing with their shells together like that. So white dwarf, which has cooled over very, very long time down to become a black dwarf. Which has never happened because it takes way longer to let the form when the universe is existing. That's according to the Cosmic Mimicry book by Mark Garnick, written on the page 48 and 49. Neutron stars. Now there were main sequence stars. They were generating an outward force. In the inside, hydrogen was pressed together, forming helium, and during that there was an outward force. So the big force for the gravitation falling on itself together, having so much gravitational force that it falls on itself together, was halted basically because there was an outward force. Then the subgiant phase came after the main sequence phase of the star sun, and where the core is contracting even more, but there's still coming something from the outside in, and when the hydrogen from the outside comes in together, there it expands again, the core is shrinking, the outside is shrinking, but then because hydrogen is pressed together, because it comes closer to the center, it's expanding again, the core is shrinking, the outside is expanding. Now we're having the next phase, the giant phase. Now the core has shrunk more and more together until it got 100 million degrees Celsius, and now the ash of a hydrogen production, previously hydrogen pressing together to get helium, is able to fuse again. So now by 100 million degrees, 10 were necessary for hydrogen, 100 million degrees, helium is crushed together, new outward force. It blows away this outward expanded subgiant thing which has expanded into a planetary nebula thing, and it blows it away and becomes a white dwarf. It blows basically away what it has, all is burned up, and the center is just shrinking more and more and more. It becomes a white dwarf. No light anymore, no heat, it cools down over hundreds of millions of years, and then it's just a thing. Neutron stars are heavier than normal suns. Normal suns are becoming then just a white dwarf. The electrons are completely standing together, and they have degeneracy, these gases degeneracy, and they're no longer falling together. All these electrons are standing together with their shells, these atoms with their shells with the electrons together. Completely pressed together, that's a white dwarf. Nothing happens anymore. If its sun was bigger, the whole thing was way bigger, and the pressure on these electron shells, was much bigger, because the star is much bigger, and now they shatter. And the electrons on the outside of these shells and the protons inside of a nucleus of such an atom are fusing together. They are pressed together and forming new neutrons. The electrons on the outside of the shells and protons of a nuclei form together, becoming new neutrons. And the whole thing exists out of neutrons. And now, when we were pressing together like that, they're getting much smaller. A normal star gets already down to Earth size, much compressed. But now they're going down to just a few kilometers, which is kilometers big, but they were massive. And now they're just very, very, very small together. And if someone is spinning and turning around and puts their arm in a figure skater on ice, they're turning faster. Or basically, if there's a long outward force and that's brought in, now that same speed is there, but on a much smaller space. I think that is the explanation for it. So basically, all this outward force, which was turning normally in such a big sun, is now very much close together. And now the whole thing is spinning very fast. The Earth is turning around in 1 day around its axis. Such a neutron star can spin hundreds of times a second. So incredibly fast. And it can have very strong magnetic fields along its axis, and they can be pushed out when along its axis, and better than pulsars. So these super amplified magnetic fields can be pushed out along the axis while it is spinning, so hundreds of times per second can be pushed out, and that is known as pulsars. And that is according to Mark A. Garlick's Cosmic Planetary book on the page 51. Black holes. A star came out of its main sequence, and then it started to shrink because on the inside there's no nuclear fusion happening with hydrogen pressing together to form new helium having an outward force. It shrinks, and then it shrinks more and more, and then it comes to the red giant phase, and there it is able, because it had shrunk more and heated up more through the shrinking together, having 100 million degrees, and now the helium can be formed together to form carbon and oxygen, again an outward force, the outward things are blown away, and now we're having just core standing basically there. It's just consisting out of this ash of helium or carbon and oxygen, and it cools down, and it goes completely together. So first that it goes completely together until the shells of the atoms are standing completely together. And now we can't move anymore. It cools down, no movement, no heat, it just cools down and gets darker over hundreds of millions of years. If that big sun at the beginning had more than 1.4 times the size of the sun, so a bit bigger than the sun, then the Houth pressure of the core is too big, and these shells of the atoms break, they shatter. And now it doesn't stay a peaceful white dwarf, just all standing like that as degenerated gas, just standing like that forever and ever, they shatter. And now the electrons on the outside of the shells are fusing together with the protons on the inside of the atom and forming new neutrons, and we're having a neutron star. And now it has already shrunk massively. It can shrink again 1,000 times more, and it goes really, really close. It's still a few kilometers, but it goes very close together, and that is a neutron star. So the whole thing consists out of neutrons, all shrunk massively together, completely shrunk together, a few kilometers, turning incredibly fast and emitting light beams and so on. But now what happens over the black holes? That happens if they have more than 1.4 times the solar mass. So the shells are shattering, it doesn't stay a white dwarf, it becomes a neutron star. If the sun was 1.4 times as big, but more than 3 times as big, then these neutrons don't hold anymore, and even they shatter. So these shells had shattered in white dwarfs, becoming neutron stars, and now these neutrons themselves are also shattering. And now it just shrinks together until it has zero size anymore and infinite density. So the whole sun, or at least the core of it, had shrunk down to become a white dwarf, and neutrons are just neutrons, and now the neutrons have shattered, and the whole thing becomes down to zero size, but it has infinite density. All is pressed out of it. And it has an incredible gravity set, the whole gravity set, and it puts everything in, even light. And that is a black hole. It's just the sun going completely down together to zero size, infinite density, an incredible gravity, pulling everything in, letting nothing out, even not light. That is according to Mark A. Garlick's Cosmic Planetary book on the page 52. The temperatures of the sun. In the core, it are 15 million degrees Celsius. At the surface, it are 5,500 degrees Celsius. And at the outer layer of the atmosphere, the outer layer is called corona of the sun, where it are 1.7 million degrees Celsius. So the core, 15 million, and the surface, 5,500. But this atmosphere up to the outer layer called corona of the sun, 1.7 million degrees Celsius. And that is according to Isabel Thomas out of his World book, page 14. Terrestrial planets are planets with a rocky or solid surface. The Earth is a terrestrial planet. They are also called telluric planets. It comes from the Latin words for Earth, terra, terrestris, or tellus. And now telluric or terrestrial planets are planets with a rocky or solid surface. In the solar system, these are a part of the Earth, also Mercury, Mars, and Venus. That is according to Mark A. Garlick's Cosmic Planetary book, page 80.
New York is 3 hours different from Los Angeles. If it's 12 o'clock high noon in New York, it is 9 o'clock in the morning in Los Angeles. The 3 laws of motion by Isaac Newton are: 1. A body remains at rest or in motion at a constant speed in a straight line unless it is acted upon by force. 2. At any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalent, the rate at which the body's momentum is changing with time. 3. If 2 bodies exert forces on each other, these forces have the same magnitude, but opposite directions.
The 8 planets from the Sun are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The Andromeda Galaxy. The Andromeda Galaxy is a galaxy. It is spiral-shaped just like the Milky Way. So the Milky Way is there, quite big, and then at one side there's the solar system, and there's then the Earth. So in the Andromeda Galaxy is a galaxy like the Milky Way. And it is the furthest object away which can be seen from Earth away. So the stars are way closer, and this Andromeda Galaxy is the furthest object away which can be seen from Earth with the naked eye. It's also the first other galaxy which was discovered. And it is 2.2 million light years away from Earth, and it is a bit larger than the Milky Way. The Andromeda Galaxy is across 130,000 light years. And it is a little bit visible under good conditions behind the Andromeda constellations, so other stars in the sky at night, where as a faint fuzzy patch can this Andromeda Galaxy be seen. And that is according to Book 1, Part 1, Structure of the Universe of the Reader's Digest Library of Modern Knowledge, written by Ian Ridpath and John R. Shakeshaft on the page 48. The asteroid belt. The asteroid belt is between Mars and Jupiter. So with the Sun, then it's Mercury, Venus, Earth, and then Mars and Jupiter, they're between, and then there come also Saturn, Uranus, and Neptune. So between Mars and Jupiter, there's the asteroid belt. And these are a bunch of asteroids just around the Sun, or they go there. They are just there. And now there are 25 million which are bigger than 100 meter, and 125,000 which are larger than 1 kilometer, and 4 of them are larger than 500 kilometers. And the biggest one of them, discovered in 1801, first asteroid discovered, is Ceres. That one is 950 kilometers in its diameter. And that is, and they are mostly out of carbon stuff or metallic or stone material. And they are basically leftover chunk from when the solar system was forming, which has not formed into planets as the other parts. And that is according to Mark A. Garlick's Cosmic Planetary book, page 21.
The calendar. The calendar is an instrument to measure how much time is passing, and it's most of the time based on 1 year. That's the time which the Earth takes to go once around the Sun, and then also a month, which is approximately the time the Moon takes once around the Earth, and then also a day, which is the time the Earth needs to spin once around its own axis. These are the basements basically for all calendars. The Sumers had one 5,000 years ago, and that was based then with the months on the time the Moon needs to circle around the Earth. The problem by that is that the Moon needs 29.5 days, and that should also fit together with the 1 year the Earth going once around the Sun. And it doesn't fit. 29.5 days gives after 12 months too little, after 13 moon months too much of a year. So it doesn't really work to make it on the Moon based, this month length of 29.5 days. It doesn't work. It's a little or too much for that whole round. And the 30 months on, it doesn't really work. Julius Caesar then was reigning 46 before Christ in the Roman Empire, and we as astronomer Sosthenes advised him to make another calendar, and that calendar looked a little different. It was based on 365 days and 0.25 days, so 365 and a quarter day, and that were 12 months, and each of them had 30 and 31 days. And then a leap day every 4 years in the leap year, there's been 1 day more. There's a little problem with it. The Earth doesn't need 365.25 days to circle around the Sun, but 365.24 days. 24.22. This is important for nothing. So the Julian calendar was a little bit off. And then in the year 1582, I think was it, when Pope Gregory VIII was the Pope, where it was off by 10 days. Now it is, so the Earth stands like that in the sky, and the Sun hits it in the summer, like that in the northern half. And now the northern half of the Earth has summer because the Sun hits directly all the cities in the north, of North America, Northern Asia, Europe, and so on. And when this Earth's on the other side, the red stands away, and the Sun also hits it, but it comes completely through the side and goes a long way through the atmosphere. And now it is winter there because the Sun is not traveling directly to it, or when it's like that, when it hits also better like that, but it goes now, as it is on the southern half in the other part, the other way around, it goes through the side for a long time, and the Sun is much colder. And also there's much less sun because it's the hotter in the shadow.
And that is the reason why there's winter, and on the southern half of the Earth it's the other way around. When Europe has here summer, the southern half has winter. It's in the shadow basically of the Earth. The other way around, when the southern half of the Earth, South America and Australia has summer, and the northern half has winter. Now, and if on the equinox the world is standing after 3 months on the 21st March or the 23rd September in the middle, then the sun hits it directly in the middle and they all have day and night the same length. Now, the problem with it was that this Julian calendar was based on 365.25 days, not 365.2422 days. It was off now by every century by 1 day. Almost, it's 0.2422. Basically, it was off then by 10 days. So it was then set on the 11th March. Now it's the middle, but it was actually at 31st March or something. It was off by 10 days. And then was said we're adding now every century, not a leap year, I think was it. So every century there's not a leap year. Every 4 years there's a leap year, but not if it's the 100th year. Not if it's 1900, 2000, 2100, 2200, except that years divided by 400. If it is 2000, 2000 divided by 400, then there is a leap day. Because it's 24.2422. The 2 is there 1/5. That's why it's off after 15 centuries when Pope Gregory VIII was there by 10 days and not 15, because it has to be done, the leap year, every 400 years. It has to be just included every 300 years, something like that. So that's why it was off. And then it was introduced like that. So there is now 365 days, 0.2522, and there are 365 days with 12 months and 31 days and 30 days. And every 4 years there's a leap year, except that is every 100 years there's not a leap year, the 100 years, except that here is a 400 year, like 400, 800, 1200, 1600, 2000, 2400 days again. And that way, one calendar was made which should work. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridworth and John R. Shakespeare, on the page 51. The celestial sphere. That is an imaginary sphere around the Earth. Or otherwise to be said, if the Earth would be that big, and where a star is searched, where would it be on the Earth? So the Earth has a North Pole at one place, and now just out of it, there is the North Celestial Pole. So just a sphere around the Earth, and where the North Pole of the Earth is, then further out in space is the North Celestial Pole. Someone could say there is a star at the North Celestial Pole. It is when where the North Pole is on the Earth, just out in space. Or the South Celestial Pole. There's a star at the South Celestial Pole, where the South Pole is of the Earth, just out in space. Or the Earth has an equator, and the celestial equator is then just where the equator is out in space. Someone could say there's a constellation of stars lying on the celestial equator. It's when where the Earth's equator is just out. Or the Earth has longitude star. For example, longitude 20, it's also the same on the southern part of the Earth, longitude 20, again just minus or something, or southern longitude, and then out in space. That's called right ascension. Someone could say there is a star at the right ascension 20, and then it would be where the Earth's longitude 20 is, just out in space. There's when the star. Or the other thing around the Earth, the lateral, they are the declination. So declination 20 or 40 million. So someone could say it is at right ascension 20 and declination 40. So we're having on Earth longitude 20, right ascension 20, and then longitude declination 40. So lateral 40, and the star would be then right ascension 20, longitude 40. There's the star, and the people there could see it. That is the celestial sphere. It's just the Earth, just when where it would be out. It's to find the stars out there. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridworth and John R. Shakespeare, on the page 52. The formation of Jupiter. When the solar system was quite new, there it was hot by the sun, and further out colder. Close by the sun, iron rocks could get firm, but icy substances not. At 800 million kilometers away from the sun at the snow line, which is 5 times far away from the sun as Earth is, there it was cold enough and icy substances could cool down. And now all these icy substances stick together and one big snowball created, and this one big snowball was the beginning of Jupiter. And it had 15 times the mass of the Earth, this snowball. And now because it had 15 times the mass of the Earth, it had a lot of gravitation and was able to pull in the hydrogen and the oxygen in its orbit. And over some 100,000 years, it pulled all the hydrogen and oxygen, hydrogen and helium towards it. And when Jupiter happened to be. And Jupiter is now there, and it has the kernel, has the size of the Earth, and had then already 15 times the mass of the Earth. And now the whole Jupiter is 11 times as large as the Earth. It is in the inside, an icy kernel, also some rocks are there, but it's an icy kernel, 15 times the mass of the Earth, with a lot of gravitation, and pulling all the helium and hydrogen towards it, so that thing is a big ball in the middle, a big gravitational point with the icy substances, and surrounded all the gases, all the helium and the hydrogen. And that is according to Mark Garlick's Cosmic Menagerie, page 40. 100 billion. The Milky Way has 100 billion stars in it. And that is according to Isabel Thomas, Out of His World book, page 30. The Oort cloud. The Oort cloud, if it exists, is outside of the universe. Now there's the Sun, and then the 8 planets, Mercury, Venus, Earth, and then Mars, Jupiter, Saturn, Uranus, Saturn, and Neptune. And now there's the big Oort cloud, maybe if it is there. And in that Oort cloud there is the assumption that there are many comets. Comets have big orbits in an elliptical form, so not a circular, but elliptical. And there is the Halley comet, and that Halley comet comes around the Sun every 76 years. Once around the Sun, every 76 years. But there are other comets who come only every thousands, millions, or billions of years probably. And it is the assumption that there may be out there in this big Oort cloud around the solar system. And that is according to Mark A. Garlick's Cosmic Menagerie book, page 27. The Sun is 150 million kilometers afar from the Earth. The light needs 8 minutes to travel from the Sun to the Earth, and the humans have built a satellite called the Solar Probe Plus, and that thing can travel with 720,000 kilometers per hour. With that thing it would take 30 seconds from London to New York, and that satellite will need 6 years to travel from the Earth, the 150 million kilometers to the Sun. And that is according to Out of This World by Isabel Thomas, page 15. There are 8 planets in the solar system, and the 4 terrestrial ones are the first 4. There is Mercury, Venus, Earth, and Mars. They are terrestrial. And then there are the 2 gas giants, Jupiter and Saturn, and the 2 ice giants, Uranus and Neptune. And that is according to several pages of Mark A. Garlick's Cosmic Menagerie book, for example, page 18. Tycho Brahe. He was born in the year 1546, and he was a person who was a lot observing and looking at the sky before the telescope was invented. And in the year 1560, so when he was 14 years old, he saw a total eclipse of the Sun, and that in particular made him very interested in the sky. In 1572, he saw a star flare and dim away. It is now known to have been a supernova explosion of a star, and that it was a star doing that so very far out of the world was a very big indicator, or even proof, that the sky is changing. There was an ancient belief dating back to Aristotle that the sky with the stars is not changing, it's all staying like that. But that there is a star far out, exploding and changing, showed that also the stars in the sky is changing. 5 years later, there was a comet, and that went basically through the planets. Now, and there was some belief that the planets are going around the Sun on transparent but more or less fixed, all those tracks, something like tracks. And if the planets would do that, then the comet would have shattered them. So there are no tracks. The comet could just pass in between them. And from 1576 and 1596, for 20 years, 1576, 1596, he worked on the island of Ven, where he built a castle and an observatory with financial help of the Danish king, he was from Denmark, to analyze a lot of stars. 1,000 did he analyze or calculated them down and did all down what he saw. And then the last 3 years of his life, he started to analyze all the data he had collected together with Johannes Kepler. And Johannes Kepler, then after he had died, Tycho Brahe, he calculated them on and proved through his calculations that the planets are all orbiting around the Sun. And that is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John Shakespeare. And on page 51, there was also written that he also attended a duel. He lost a part of his nose. Walter Bode, born 1893. He was studying the Andromeda Galaxy, another galaxy from the closest one to the Milky Way. It's still far away, but it's the closest galaxy. he was studying it, and where he was seeing two stars, he was studying them. And these were Seyferd variable stars, so stars which are getting brighter and dimmer. They are varying in size, they're getting brighter and dimmer. Now, and they're doing it in fixed periods. They're doing it between some days and a few days. Maybe one takes 5 days, maybe one takes 50 days. So it gets brighter and then dimmer. And a person on the Earth can just look how long does it take to get brighter, 5 days, and dimmer 5 days. And now it's 10 days for one period. And it is possible to calculate now how bright the star is, just because of knowing how long the period was. If it was, the longer the period is, the brighter the star is. So it's possible with 10 days to say it has this brightness. If it's 20 days, that brightness, 30 days, that brightness. So from that, through observing how long the period is, it is possible to know how bright that star is. A star is bright, but on the Earth it is dimmer. A star is a sun, so the sun on the Earth is a very bright star. It's very bright from the sun. The other stars are very much darker. In the night, even in a starry night, the stars are giving basically no light at all. But these are all just stars, so there's these suns. All these suns in the night sky, in a starry night, are all suns. They are very bright, but on the Earth only a little bit of a light appears. It is now possible to look now how bright such a star is now on the Earth, how bright appears it. It is actually much, much brighter. It's just very, very far away. So it is now possible to look by such a Seyferd variable star, how bright appears it on Earth. Just very, very, very dim. If at all with a naked eye, very dim. But we know from calculating how long the period was, 5 days, 10 days, how bright it actually is. And now by comparing this, how bright appears it on Earth, just very, very faint, and how bright is it actually, because we know how bright it is, because the longer the period is, which is getting brighter and dimmer, makes how bright it actually is, how far it is away. So we can calculate how bright it is, because we know the period to get brighter and not so bright, and we can measure how bright it is on Earth a little bit faint. And now we have the distance. Walter Bode did that with 2 stars, and he found out that the Andromeda Galaxy is actually double as far away as believed. The star previously used wasn't completely proper, or the assumption wasn't completely proper. He found out the Andromeda Galaxy is 2.2 million light years, 2.2 million something away. And so this is double as much, and then other distances in the universe were as well recalculated based on it. So Walter Bode was studying the Andromeda Galaxy, 2 Seyferd variable stars, how they're getting brighter, how far they're actually away, calculated it is actually double as far away, and all the other things were also recalculated. That is according to a Reader's Digest Library of Modern Knowledge, Book 1, Part 1. Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakespeare, on the page 50. Walter Sidney Adams, born in 1876, lived until 1956. He worked out an important method to measure the distance of stars from the Earth. And it was done with comparing the absolute magnitude, how bright the star is actually, and how big the apparent magnitude is of a star on Earth, so how bright it appears on Earth. And that did he do with looking on the spectrum, some things. Now, there's the explanation missing. I think it's the following, that there are different types on the spectrum of the electromagnetic spectrum, and there can be gamma rays or radio waves, and some of them are long and reaching the Earth. And I think now that the star is emitting just all these different types of light and rays, ultraviolet and microwave and infrared and whatever all. So, and just some of them reach. And by looking, it have reached this, or this rays of light have reached Earth. It was able to say it's so and so far away. But I don't know, it's not explained if it is the case. I don't even know if it is possible to do it that way. But that first part was according to Structure of the Universe of the page 48 of the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, written by Ian Ridpath and John R. Shakespeare. The reason why the moon appears to have the same size as the sun from Earth was seen is because the sun is 400 times further away than the moon. And now because the sun is 400 times further away, even though it is around 400 times bigger than the moon, it appears to have the same size seen from the Earth. Now, and I'm going to show it in a moment here. There's this football, which is around 5 times as big as a tennis ball. And now this football is around 5 meters far from the camera. We go now closer, and this tennis ball is now 1 meter away from the camera to the football, when they appear to have the same size. And now also, like a solar eclipse, the moon can come before the football and block it. So that's all. And that was according to Out of This World by Isabel Thomas, page 30.